Good evening, and thanks for joining our Tuesday webinar hosted by Texas Instruments. I thought I knew everything there was to know about the golden mean, and I have a feeling that our two presenters tonight are going to prove me wrong. My name is Mike Houston, and I'm the moderator for this event. I teach algebra and calculus near Pittsburgh, where I use TI technology to make tough-to-teach, tough-to-learn concepts accessible to all our students. And today I'm joined by our two panelists, Ray Barton and Troy Jones. Ray has been a T-Cube national instructor for many years. He teaches AP statistics and middle school algebra and has helped develop many T-Cube workshops. He enjoys using graphing technology to make mathematics accessible and interesting for students. He currently teaches at the Waterford School in Salt Lake City, Utah. Ray, it's great to have you with us tonight.
Thank you. I'm excited to be here.
And Troy teaches math at Westlake High School as well. If you have been to if you have been to the Park City Mathematics Institute in the past 20 years or so, you probably have seen Troy in the teacher leadership program or running the summer math camp for high school students. When not spending time with his family, Troy enjoys thinking deeply about simple things and seeing the world with new eyes. Troy, it's great to have you with us.
Thank you. I am excited to share my passion.
And Ray, will you please discuss our agenda for tonight?
Yeah, so we're going to begin with just a brief introduction to the golden mean for the few that may not be very familiar with it. Then we'll look at a few of the better known appearances of the golden mean. But then we're also going to look at some newer appearances and some that could be a bit surprising. We're also going to try something called the magic word. If you watched Steve Phelps in the webinar a few weeks ago, when he did the Monty Hall problem, they tried this magic word idea. When we ask a question and we'd like you to send in your answer in the chat window, rather than just immediately sending in your answer, we're going to have everyone pause for a few seconds, for maybe 20 seconds. And then when I say the magic word golden, then go ahead and submit. That way, everyone will have a chance to submit answers without seeing other answers beforehand. So it's kind of a fun way to get everybody to submit together without being influenced by other people's responses. And then remember, at the end of the webinar, Michael will be conducting a drawing for a TI calculator.
Thanks so much, Ray. And Troy, would you talk through some of the expected outcomes for tonight?
Yes, so as Ray said, we want to share things that we think are really interesting, but we can't share everything. There's so many cool things about the golden ratio. So we're hoping that by the end of this webinar, you'll understand how the golden mean is defined, that you can recognize it in a variety of settings, and that you just enjoy the beauty of the golden mean and the amazing places where it pops up. So that's what we'd like to have happen.
Awesome. Thanks so much, Troy. We're expecting a large crowd, so your audio is muted. Feel free to send any questions to Troy or Ray using the Q&A window on the right side of your screen. And as Ray mentioned, we are going to be using the chat window tonight. And again, you can go ahead and type your responses in whenever they ask questions, but hold on and hang tight before you press the enter button. Wait for that magic word. As a reminder, this session is being recorded, and we'll provide a link to the event certificate of attendance at the conclusion of the webinar. So Ray, without further ado, let me give you control.
Thank you. So I'm going to share my screen, and let's just begin with something probably most of us know about, but just kind of to get caught up, just the basic definition of the golden mean. It's a ratio, so it's sometimes also called the golden ratio or the divine proportion. If you divide a segment into two pieces, A and B, then the sum of the two pieces is A plus B.
So Ray, I don't think you're sharing your screen.
All right, let me jump back and see what happened there. Sorry about that. I had two buttons to click, and I think I only clicked one of them.
There you go.
Okay, thank you. So, A is A. So here's my segment. I hope you can see it now. A plus B is the sum of the two, and that ratio is to A as A is to B. And so if we replace the A with X and the B with 1, then we get this second line, X plus 1 over X is equal to X over 1. And sometimes the letter that's used for that golden mean is phi. And if we solve that equation for X, we get an exact value of root 5 plus 1, or an approximate value of 1.618. And you're going to see those pop up tonight. So be watching for those two values. And then secondly, just quickly want to define a golden rectangle. And that's simply a rectangle where the ratio of the long side, A plus B, to the short side, A, is golden. So Troy, I'm going to hand this off to you now to do to show us a construction, I think is what you've got in mind.
Okay, perfect. So let me, when I grab control here, I'm going to share my screen. Okay.
Great, I can see your screen.
Great, so I'm on the TI-84 and I just want to show that decimal approximation. So I typed in the exact value, and when I hit enter, it's going to evaluate that expression and store it to the Greek letter theta. That's the closest I have on my calculator to phi. So I'm just going to call theta phi when I refer to the golden ratio. So this is an approximate value of phi. Now there's two interesting powers of phi that I'd like to look at. So let's look at phi squared. And get ready to answer this question when Ray says the magic word. I'm going to show the approximation of phi squared and see if you notice any relationship between phi squared and phi. So there's phi squared.
Okay, so what do you notice about those two, the relationship between phi squared and phi? Go ahead and type your answer into the chat window, but don't send it until I say the magic word. So let's give everyone a chance to type in what they noticed about the connection between phi squared and phi. Okay, and the magic word is golden. Go ahead and send in your answers to the chat window.
I'm seeing a lot of responses that look very similar.
All right.
So most of you noticed, and some of you commented, that phi squared is one more than phi. And that is really one of the defining characteristics of phi. It's the only number that when you square it is one more than itself. And one more power of phi that I'd like to look at, the reciprocal of phi. So I think if I take the reciprocal of phi, 1 divided by phi. Again, let's do this chat. So Ray.
All right, what do you notice again? How is 1 over phi related to phi? And the magic word in just a minute is golden. Go ahead and hit enter to send in your response.
So yes, a lot of people notice that phi, the reciprocal of phi is 1 less than phi. And again, that's characteristic of the number phi, the only number whose reciprocal is 1 less than itself. So when you square phi, it's 1 more than itself. When you take the reciprocal phi, it's 1 less than itself. And so
I noticed someone said, what about phi cubed? I really wish we had time to do that because it's pretty amazing too. But we've got so many other things to do that we might not get that far tonight.
All right, so I'm gonna, on the TI-84, I'm gonna go into an app called Cabri Junior. And this is a dynamic geometry environment. And so when I enter this application, I've already created a construction. And so what I wanna do is I wanna go through this construction, but there's a nice feature. The F1 button has these menus, and under the undo menu, there's an option called explore. And so when I run this explore feature, it's going to step through the construction that I already created. And so I want to partition a segment into the golden ratio that Ray defined. So I'm going to start out by creating a segment AB, and then we want to find a point on AB that divides this segment into that special ratio. So the way that I'm going to do this is I'm going to construct a right triangle where the two legs are in a 1:2 ratio. So this is going to be the long leg. So I'm going to find the midpoint of this segment and then construct a perpendicular and transfer that length up here. So I've got point C, and that is half as long as AB. So if I call AB 1, then BC is a half, and by the Pythagorean theorem, the hypotenuse is square root of 5/2. So I just labeled 1 for the length of AB, a half for BC, and then here's a decimal approximation for the square root of 5/2 for the hypotenuse. So what I'm going to do now is I'm going to take that length 1/2 and transfer it up to the hypotenuse. So I've got point D, and the length CD is a half, and so the length AD is that entire hypotenuse minus a half. And so if I take that length of square root of 5/2 and subtract a half, I get that value right there. And maybe you might recognize that from our previous screen. And then if I transfer that length down to segment AB, I find a point P, and the length AP is that 0.618, which is the reciprocal of the golden mean. And so if I take the entire thing, so the definition of the golden mean was if we take the entire segment AB and divide it by the longer part, AP, in this case, if I have a 1 divided by the reciprocal of phi, that's equal to phi. So that point P divides this segment into the golden mean. So I'm going to exit Cabrit Jr. and go to the TI-Nspire. And here is a skeletal view of an icosahedron. Now, in the TI-Nspire, I created this in the 3D window, and I can manipulate this. In fact, I'm going to just choose auto rotate. So we have the skeletal view of the icosahedron, and I've labeled or I've colored a couple of opposite edges. So a pair of red, in red are a pair of opposite edges, in green are opposite edges, and in blue are opposite edges. If I connect those opposite edges that correspond to the colors, it forms a rectangle inside of the icosahedron. And I can construct all three of these rectangles. And it's kind of hard to see with the edges of the icosahedron. So I'm going to change the background color to black, so we'll kind of not see the black edges of the icosahedron. But here we just see the three rectangles inscribed in the icosahedron. And it turns out that these rectangles are golden rectangles. The ratio of length to the width is the golden ratio. And these three rectangles are mutually perpendicular to each other, inscribed in the icosahedron. So Ray, I'm going to turn it back to you. So
okay, thank you. That was an amazing animation. Thanks, Troy.
You are welcome.
Okay, let's see if I have better luck sharing my screen this time. Can you see it this time, Troy?
It looks like it's starting to share, yes. Continued roots.
Okay. So we're going to see what continued roots have to do with the golden mean, but there's also a backstory here. This, you might be wondering what this has to do with the story. This was my first calculator, and then this may age me. You might be able to figure out how old I am, but this was a Summit calculator. It was as big as a brick. It ran off a 9-volt battery. And I thought I was the coolest kid in school when I had this calculator. Even though it only did basic arithmetic, as you can see from the front keyboard. But what made me ultra cool was there were these plungers on the top, and the plunger by that blue arrow would take square roots. So whatever number was on the display when I hit this plunger, it would take the square root. And of course, you know what a teenage boy is going to do with that. He's going to press it again and again. And I didn't realize it at the time, but I was doing a continued root by taking the square root of the square root of the square root. but I didn't realize it was a continued root, but I did notice a pattern that didn't seem to matter what I put in, it converged to 1. Well, you can do this on a TI-84. There isn't a plunger button anymore, but you can accomplish the same thing with a feature called the answer key that allows us to store the most recent calculation. And then we are also, after we try that, we're going to try another continued root where instead of just taking the square root over and over, each time before I take the square root, I'll add 1, and we'll see what happens there. So let me jump over to my TI-84. So Troy, can you see my TI-84
Yes,
now?
I can see it, yes.
Great, thank you. So I start with a big number, and when I press enter, it stores it in a variable called answer. And I have access to that if I press second and then this negative key. So I'll take the square root of answer, and that's right now it's 10,000 is stored in answer. If I take the square root, then I get 100. And now the beauty of this is I don't even have to type in square root of answer again. If I press enter, it just repeats that calculation.
And you don't even have to press the plunger.
Yeah, so that red enter key has become my plunger key. And now answer is updated with the value of 100. So when I press enter, it takes the square root of 100. Now when I press enter, it'll take the square root of 10. And so I just keep pressing that, and we see convergence to 1. So now I want to try it again with that other continued root. So I'm going to reload 10,000 into my answer key. And now I'm going to do the square root of 1 plus answer. So I'll be taking the square root of 10,000 of 1, which is just a little bit off from 100, but not much. And now when I press enter, it'll take the square root of 1 plus 100.004999. So pretty close to 10. So another question for you, and wait to put your answer in the chat window as soon as I say the golden, give you the password of golden. But what do you think this will converge to? If I continue to hit that enter key over and over, what kind of convergence do you think we'll get? So let me give you a few seconds to just think about that and then load up your answer. And then when I say the magic word, we'll get a bunch of answers in the chat window that we can compare with each other. Okay, so Golden, go ahead and send in your answers into the chat window. Let's see what happens.
Well, I'm seeing 2, 3, and oops, we're still getting used to the golden password here. 1, fee,
Okay.
golden.
Let's try it and see. So let me keep hitting the enter key. It does look like it's creeping down. Now, first when I did this, I thought, well, it's creeping down towards 1, but I can't seem to get it to go below this 1.618. Eventually, I think the decimals won't change because it will have converged to, yeah. So Troy, do we recognize that 1.618?
I recognize that. One of my favorite number.
Okay, so that continued roots converges to 1 plus, or that square root of 1 plus answer converges to the golden mean. Wish we could, we're saying this a lot tonight. I wish we had time to prove why this works, but right now we're just being amazed that it works. The next thing I want to show you is a connection with the golden mean and Fibonacci numbers, and then a formula for the Fibonacci numbers. So Troy, can you see my TI-Nspire now?
Yes, I see the tables.
Okay, great. So in the first column, I have a sequence called the Fibonacci sequence, which I imagine most of us have seen before. It starts out with 1, and then the next value of 1 is 1, and then the next value is 2. And the way you get a value is to add the previous 2 terms. So 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, and so on. And then I wrote the Fibonacci sequence again in the second column, but I advanced it by one value because I'm going to take Fibonacci 2 and divide it by Fibonacci 1. So think about what's going on here while I type it up. So Fib 2 divided by Fib 1. What I'm really doing is taking a number and dividing by the previous Fibonacci number. Like down here where my cursor's wiggling, I hope you can see, that will divide 5 by 3. Then on the next one, it'll divide 8 by 5. So we're seeing what happens when we divide a number in the Fibonacci sequence by the previous value. And as we scroll down, we see those ratios converge to phi. And this is a pretty well-known result, that there's this deep connection between Fibonacci numbers and the golden mean. If you take a ratio of 2 consecutive Fibonacci numbers, you get something close to the golden mean. And in fact, those ratios converge to the golden mean the further out we go. So Fibonacci numbers are a big deal, and they're connected to the golden mean. And so here we have, on this next page, a function that I've defined as Binet, because it's called Binet's function or Binet's formula. And this function gives you Fibonacci numbers. So if I put in 1 to this equation, I get 1. If I put in 2 into the Binet function, I get 1. If I put in 3, I get the third Fibonacci of 2. So I put in a whole list of values, because you can pass a list into a function. And it gave me the first 10 Fibonacci numbers. So I'm just demonstrating that this Binet function gives you Fibonacci numbers. And notice that it involves 1 plus root 5 over 2, which is the golden mean, and then 1 minus root 5 over 2, which is the negative of the golden mean, of the reciprocal. So what I want to think about is, what would happen if we put in negative numbers? You can't really have negative ordinal values, but nevertheless, now that we've got this function that pumps out Fibonacci values, what if we put in negative values? So let's try that. So I put in the numbers -1 through -10, and look what I get. Once again, I get Fibonacci values, but it looks like the signs oscillate between plus and minus. And now that we've gone, a little bit unconventional by putting in negative numbers, here's the next question. What if you put in a fraction, like 0.5? Is there such a thing as a 0.5 Fibonacci number? So I put in Binet of 1/2, and this made me, I was surprised to see this. You get complex numbers. And so Binet of 1/3 is another complex number. So, I guess I could ask you the question, Troy. So are these Fibonacci numbers because they came from the Fibonacci formula?
Well,
So,
I don't know.
Complex Fibonacci numbers? I don't know. I'm not. I guess maybe it's up to us to decide.
That's not a real
So
question.
what I want to last of all show you is a graph of the Binet function, not just for the whole numbers, but for the real numbers. So what would a graph of Fibonacci numbers look like? And it's a really kind of an elegant little curve here. So what I graphed is the x-coordinate of each point on the curve is the real value of the Binet function, and the y-coordinate is the imaginary value. And this is for values of t that are positive. And wherever it crosses the x-axis would be an actual Fibonacci number. So notice it crosses at 1 twice, then it crosses at 2, and then at 3, and then it crosses again at 5. So you can see the curve crossing the real axis at the Fibonacci numbers. And then last of all, let's see what it looks like for negative values. So here I did negative values for t, and we get this spiral, but once again it crosses at the Fibonacci numbers, but we see that alternating pattern with the positives and the negatives that we had a few minutes ago. So that's kind of a brief introduction to Binet function and what the graphs look like. So now, Troy, I'm going to hand this back to you to show us. I think Troy's going to show us some fractals.
That is so cool, Ray. I just have chills looking at that.
It is a pretty curve, isn't it?
It is.
All right, let me pass the ball back to you.
Okay, so when I get control here and share my screen, we're going to talk about a fractal. Now, fractal is just a simple pattern that you can repeat over and over again. So let's see. Okay, so what you're looking at here is I've got a circle with two chords drawn, so I have a central angle of 90 degrees, and that allows me to drag and control the angle. And then I've got a segment, and under the segment you see 0.25. That's as close as I could get to 0.25 or 0.254. So the resolution and just the way I constructed this, I'm not going to get exact values, but I'm going to get approximations by dragging things. And so I'm taking a segment, this red segment, and I'm rotating it by 90 degrees to the left and to the right, and scaling it by a factor of 0.25. And then I just iterate that process. And so that's just a simple branching fractal, rotating by 90, scaling by a quarter, rotating by 90, scaling by a quarter. And so if I drag this scaling factor, we could change the scaling factor to different values. I could drag it all the way to 1. If I rotate by 90 degrees and scale by a factor of 1, we get this tiling of the plane, square tiling of the plane. And so we could drag it to any value we wanted to, but we might, want to know the question, what would I have to drag it to for the two branches on the left and the right to converge in the middle? So kind of experimentally, we might see a value. And this was hard to create, so I created a couple more iterations right here in the middle, but it'd be interesting to, instead of 90 degrees, is to change this to a different angle. So we see some interesting patterns, these kind of tree looking things, or broccoli. So we could change the scaling factor and change the angle. So I want to rotate by 120 degrees. That's a nice angle. And if I were to scale this by, say, 1, this is a hexagonal tiling of the plane. So what do you think I would have to scale this by for the two branches to converge in the middle? Let's do that golden question again. So
Troy, by converge, we're trying to get the branches to sort of touch each other eventually.
touch each other in the middle, yes. So if you thought about it, I'm going to say golden. Go ahead and send your responses in. What scaling factor would cause the two branches to meet in the middle?
And somebody answered your golden with another golden.
All right, so I'm just going to drag this, and experimentally, I can see that when I get,
it looks like it about touched.
Yeah, I'm not going to be able to drag it exactly there, but that's pretty close. And the exact value would actually be the reciprocal of the golden ratio, 0.618. If I could drag it to exactly that and do enough iterations, those two branches would converge. And that's a nice little proof you might want to try to prove that that really is the case. And one more document here. So what we're looking at here is a crescent shape or a loon. So I've got two circles that are internally tangent to each other at point C. And the red circle, I'm cutting out part of the red circle with that white circle. So the radius of the red circle is A, the radius of the white circle is B, and I have this crescent shape. And I've constructed also the center of mass, X bar. So if I could drag B so that I'm not cutting out anything, the center of mass of the crescent shape would be the same as the center of mass of the circle at the center of the circle. It would balance at the center of the circle. As I start to increase the radius of the inner circle, the center of mass starts to move away from A. Now, sometimes that center of mass...
The center of mass is X bar?
X bar is the center of mass. Sometimes the center of mass is on that shape. If this were cut out of, say, cardboard, I could balance it at that place. But sometimes that center of mass would be out in space. And I'm thinking of a boomerang. If you were to throw a boomerang, it's going to rotate or revolve about its center of mass in space. So
did you say, Troy, that red thing is called a loon?
Yes, some sources call it a lune, some call it a crescent. But the interesting thing is, as I watch the center of mass, as I drag this so that the center of mass is on the circumference of that smaller circle, you notice up in the left-hand column, or the left corner, I've got the ratio of the diameters, or the ratio of the radii, and I see that golden mean again. So when the center of mass of the crescent shape lies on the circumference of the inner circle, it divides the diameter of the outer circle into the golden mean. To me, that's just amazing.
I love that construction, Troy. So the one you've got now, that should be a golden lune.
That's right. Okay, I'm going to turn the webinar back over to you, Ray.
Okay, great. We're going to look at some matrices for a minute, but I've noticed in the chat window, some people have been asking what software we're using for these different demonstrations, especially for the stuff that Troy has done. They are constructions he's done just on TI-Nspire software, or you can do it on a TI-Nspire calculator.
You can do it on the handheld or the computer, yeah.
Yeah, and these documents we've put them all in a Google folder, and there's a link to that Google folder that you'll be getting with all of your documentation. So yeah, if you want to play more with these Nspire documents, as long as you have an Nspire calculator or Nspire software, then you can go back and play with that lune or the icosahedron and all of these other amazing things that Troy has constructed. Oh, okay, so Troy, can you see my TI-84 now?
Yes, I see your home screen.
So we're going to switch gears. This isn't quite as fancy a visualization as the constructions Troy did, but we're going to see how a particular matrix has the golden mean hidden inside it. So I want to show you the matrix menu on a TI-84. So if I press second and then the reciprocal key, you see that there's the word matrix above it in blue. So that's the matrix menu. And the first thing I'd like to do is edit a matrix so I can put some values into it. And it's going to be a 2x2 matrix. And I want to put in the values 0 in the upper left-hand corner, and then 1. And if I jump down to the bottom row, both of those values will be 1. And so that's my matrix. Now if I quit to the home screen and then just pull that matrix up again, so this time I don't need to edit it because it's loaded. So I'll just type number 1 to paste A back. When I press enter, we can just double check that I've got what I want there. And what I want to do is start, first thing I want to do is square this matrix. So the way I can do that, one way to do it is to pull up A again. And I could multiply it by A, but instead I'm going to multiply it by answer. So think for a minute, what would be stored in the answer key? We used this when we did some continued roots a little while ago. So, and we had numbers stored in the answer key or the answer variable. Now we have a matrix stored in answer. So this is going to do A times A. So if you're really good at matrix multiplication, think about what we'll get. If not, we'll just press the enter key. And I guess this is like my plunger experience with my Summit calculator again. I want to just keep pressing enter over and over. So if I press it one more time, then what happened here? I think now I've got A cubed. If I press it again, that's A to the 4th, and then A to the 5th. And do you recognize those numbers?
Golden.
Yep. Yeah, Joshua says they're all Fibonacci numbers. So the golden mean is buried in there now. So we've got 34 and 55. So if I do 55 divided by 34 by the bottom two values in that matrix, yeah, we're sneaking up on the golden mean because we're getting Fibonacci numbers. So as I continue to do higher and higher powers of that original matrix, we get the Fibonacci numbers, which means the golden mean can't be too far away. All right, let me hand it back now to you, Troy.
All right. So here's another one of my favorite appearances of the golden mean in a square pyramid. So,
Sorry, Troy, I'm just fumble fingers here, but I'm getting you the ball.
okay, so again, this is another document I created on the TI-Nspire. So I have a square pyramid, and I'm going to animate it because that's fun to kind of watch it here. But I've highlighted a face, so one of the lateral faces in green, and then I've taken the height and squared the height, or created a square on the height, and I've highlighted that in blue. So then off to the side, so I've got the rotating pyramid in 3 dimensions, but I couldn't measure and do things, so I had to go back to the 2-dimensional, and I split my screen. So here I constructed the triangular face and the square of the height. And the question I want to ask is, what happens when those 2 areas are equal to each other? So I've dragged a slider here, and I can increase the height of my pyramid, and you see the corresponding polygons and their areas. What happens when those areas are equal to each other? So I'm watching the dynamic areas, and as I drag the height, it's about as close as I can get right there. So when the area of a face is equal to the square of the height, we see the golden mean. And this is a special pyramid. I constructed the base edges, the square base edges, to be a length 2. But any scaled version, you can scale this, because the golden mean involves ratios. When you scale these and form ratios, you'll always get the golden mean no matter the scale of the figure. So the golden mean appears in this figure when the area of a face is equal to the square of the height. And I've highlighted a cross-section triangle. I think this little red triangle. We're going to see that red triangle come appear a little bit later on. But I'm going to hand this back to
So
Ray.
just 1 second, Troy, before you do that, just to kind of to iterate the answer about if we want to get this software, what can we do? So this Troy has a document you can see down here in the corner. It's called T3 Webinar Troy. And that document is a TI-Nspire document that's going to be in the Google folder. So all of these different constructions that he's done, I think he's kindly sharing with us in that Google document that you'll get a link to.
Yes. All right, Ray, it's yours.
Okay, we're going to switch, I think, to some calculus now. So this is maybe one of the most recent discoveries of the golden mean that I've seen. And so this one just is one of my favorites, I guess, because I teach calculus. But so Troy, can you see my 4th degree polynomial
Yes.
now on my TI-Nspire?
I can see points A and B. I don't think B is necessarily on the x-axis.
Right. It could be, but not necessarily. So shout out to the discoverer of this next amazing appearance of the golden mean, a math teacher named Lynn McMullen, and I believe he teaches in Hawaii. I think he's a high school teacher in Hawaii, and he discovered this remarkable connection with quartics, with 4th degree polynomials, and the golden mean. And to illustrate it, we've got just a kind of a general quartic with a couple of turning points, and A and B mark the inflection points of this quartic. And then XA and XB are the other 2 places where the line connecting the inflection points intersects the 4th degree polynomial. And so Lynn was looking for connections between these intersection points. And he said if he had just done a general polynomial and then found the intersection points, he probably wouldn't have discovered any connection between them. But instead of doing like an all-purpose general 4th degree polynomial, he built it with inflection points at A and B. So he's kind of sort of reverse engineered this. So I've got some commands to sort of show you how he built this. So first of all, he defined a 2nd degree polynomial. That's my top line here, to be x minus a times x minus b. So that would be a second degree polynomial with roots at a and b. And think what would happen if we integrate that. So there's the algebra of integrating it into green. And then we'll add a constant. And so on my third line down here, I've got that third degree polynomial plus a constant. And then I integrate that again. And now I've got a fourth degree polynomial, x to the fourth, and then this third degree term, and then a second degree term with coefficients involving a and b, and then a cx. Then I'm going to add a d to that. So that's my my general function. F at x is this fourth degree polynomial, x to the fourth minus a plus b over 6 x cubed plus a times b times x squared over 2 plus cx plus d. And that fourth degree polynomial has inflection points at a and b because of the way we built it. If we took derivatives and went back up the chart, we'd get that original, we'd get this original second degree polynomial and roots at a and b. So here's our fourth degree polynomial with inflection points at a and b. And now let's construct the line that goes through those inflection points. So f at b minus f at a over b minus a will store an m. But this computer algebra really hides, there's a lot going on in the background that you can hardly appreciate unless you try doing this with paper and pencil. Because that's the simplified version, Troy, of doing f at b minus f at a over b minus a.
And it's even got a warning sign.
Yeah, and I'm just going to throw caution to the wind and proceed anyway. So that's the slope m, and then f at a is we're doing a point slope formula, and so there's the line, and then here's like the big finish, and now I want to see where they intersect. And boy, this really there's a lot of algebra going on here, but so where they intersect, it looks like there are a couple of intersections. One is a times root 5 plus 1 over 2 minus b times root 5 minus 1 over 2. Looks like there's another one involving some of those roots. I think the golden mean's involved here. And then the last couple values are just a and b, no surprise there. And so what Lynn discovered is that the xa, that leftmost intersection point, is the golden mean times a plus the reciprocal of the golden mean times b, and then the other one is just I think I've got a typo there. I'm gonna have to, I thought I fixed that. Anyway, the golden mean, I think I need an A down here at the bottom, but the golden mean pops up of all places in quartics and inflection points.
Oh, wow.
The next example I'm going to show you is not nearly so complicated. We're just going to we're going to do some more calculus, but we're going to find the area under the cosine curve. So it's area bounded by the cosine and the x-axis from 0 up to b, and my TI-Nspire will do that integration to find that area, and I've got it printed over here. And watch what happens as I drag this point B closer and closer to where the tangent intersects the cosine. And sure enough, it looks like it's about as close as I can drag it, but it looks like it's golden. That's why I made the area sort of golden. So the area under the cosine curve, right, from between the cosine curve and the x-axis, from 0 up to this intersection point is 0.618. So 1 minus the golden mean. So just some couple of fun examples from calculus. And then I think Troy is going to show us another connection, why this intersection point is important. I wish we had more time to talk about why all these work, but that would take a couple more hours.
All right, Ray. Well, all this talk of cosines and tangents, it just reminds me of a right triangle. I love geometry. So when I saw this result that Ray shared, I thought about the right triangle. So here I've constructed a right triangle, and I'm referring to vertex A. So this angle A is now a 61-degree angle, and I'm looking at the cosine of that angle and the tangent of that angle. And so when Ray graphed the cosine curve and the tangent curve where they were equal and found the area under the curve, it turned out to be the golden ratio. And so I'm going to drag this triangle here until I see the cosine value and the tangent value being the same. So looks like about right there. So the cosine of this angle, and the angle turns out to be 38.2 degrees. The cosine of the angle is 0.79. The tangent of the angle is 0.79. Here at the bottom, I've got some other ratios. The sine of this angle A is the opposite over the hypotenuse. It turns out to be 0.62. And again, because of
Which
the
I'm
resolution,
guessing must be close to 0.618.
it is. And then the reciprocal of the sine is the cosecant, and the cosecant is the golden ratio. So we have the cosine, or the cosecant of that particular angle is 1.62, the golden ratio. And then the sine is the reciprocal of the golden ratio, one less than the golden ratio. So here, this triangle, actually, when I pointed out before, I have this little pyramid up here. That little cross-section triangle that I showed you in that special pyramid is the same as this triangle right here. And this triangle was well known back in the 1500s, 1600s. And so my next slide, that triangle is called the Kepler triangle, named after German mathematician and astronomer Johannes Kepler. He probably, I don't think he was the first one to discover it, but he was interested in this triangle. And in fact, in his studies, he really liked the Pythagorean theorem and the golden ratio. And he has this quote, "Geometry has two great treasures. One is the theorem of Pythagoras, the other the division of the line into extreme and mean ratio. The first we may compare to a mass of gold. The second we may call a precious jewel." So this triangle has some interesting properties, this Kepler triangle. Again, you can have a whole family of triangles that are similar to this. You can scale this by any scaling factor, but I made it so the short leg is 1, and the long leg would be the square root of phi, and the hypotenuse is phi. And so in that pyramid, if you take the ratio of the slant height divided by the short leg, that's phi. That's where we saw phi appear. And that's how you'd find the area of the lateral face. And if this is the height of the pyramid, the square root of phi squared is phi. So I'm gonna make the connection with the Pythagorean theorem. If I build a square on each of these legs, then the area of this square on the short leg is 1. The area of this square is phi, and the area on the hypotenuse, the square on the hypotenuse is phi squared. And so by the Pythagorean theorem, the sum of the squares of the legs is equal to the square of the hypotenuse. And that is the defining characteristic of the golden mean, right? The only number that you can square that's one more than itself. And we see that in the Pythagorean theorem applied to the Kepler triangle. Okay.
I love that.
Let's look at another instance here. Can 3 lengths in geometric progression make a right triangle? So if I just pick out a number and multiply by some factor and then multiply that same factor, I can create a sequence of 3 numbers in geometric progression. And I want to know, can I make a triangle out of 3 lengths in geometric progression? So again, A could be anything. We could simplify this by letting A be 1. But what I've created here is a slider that's right now set for a scaling factor of 0.5. So if I take A and multiply by 0.5, then this is half of that, and multiply by 0.5 again, and this is a fourth of the original thing. And so the 3 numbers, 1, a half, and a fourth, form a geometric progression. And up here, I've got the ratio of the last term to the first term, and you can see that ratio is 0.5. This last segment is a quarter of the original segment. So I can drag this scaling factor. What if I scale this by a factor of 1? all three numbers would be the same. Well, I could make an equilateral triangle with those three lengths, but I can't make a right triangle with those three lengths. The hypotenuse is too short. But what do you think the scaling factor would have to be to form a right triangle where the three sides are in geometric progression? I'm going to say golden. You can send in the answer in the chat window. And of course, since this webinar is on the golden ratio, then you're probably right.
Yep, they're picking this up quickly.
Now, if I drag, the scaling factor is actually 1.27, which is the square root of phi. So if I take this to be 1 and multiply by the square root of phi, I get this length, and multiply by the square root of phi again, I get phi. And that turns out to be the Kepler triangle. So the three side lengths in a Kepler triangle are in a geometric progression. And that's the only triangle that has that condition other than the family of triangles that are scaled versions of the Kepler triangle. And one other thing I want you to notice is the areas of the squares are also in a geometric progression. If I take 1 and multiply by phi, I get this area, and multiply this by phi, and I get this area, phi squared. So not only are the side lengths in geometric progression in a Kepler triangle, but the areas on the sides are in geometric progression, which is pretty amazing to me. So
that's great.
Let's see, how close are we? Okay, I'm gonna wrap up with maybe two more examples.
Okay, yeah, we've got maybe 5 minutes left before we need to hand it back to Michael.
Okay, so the Pythagoreans studied, they combine numbers in different ways, and there are three what's called Pythagorean means that they were interested in. The arithmetic mean is when you add the two numbers and divide by 2. That's an average. We talked about average. That's an arithmetic mean. The geometric mean is when you multiply the two numbers and take a square root. And then the harmonic mean is defined to be the reciprocal of the average of the reciprocals of two numbers. So if I take the reciprocal two numbers and average those, and then I take the reciprocal of that, that's the harmonic mean. And so all three of these ways of combining numbers kind of gives you a measure of central tendency if you want to find a number between these two numbers. So I've created this construction where I have two numbers, m and n, two lengths, what I'm saying, m and n. And then I've constructed the segment. So this segment here is the arithmetic mean of m and n. This is the geometric mean of m and n, and the harmonic mean of m and n. And I want to know, can I make a right triangle out of the three Pythagorean means of some numbers? As I drag point P, I'm changing the lengths of m and n. And you can see there's only one place where these two numbers, so there's only these two numbers that when I formed all three Pythagorean means, it makes a right triangle. And if you look at the ratio, I've formed the ratio, the harmonic, arithmetic mean and harmonic mean, that'd be the hypotenuse over the short leg. That turns out to be the golden mean. That also is a Kepler triangle. Now, all the years I studied the golden ratio, I can't believe I never heard of the Kepler triangle. And all of a sudden I run into this Kepler triangle, and it has all these amazing properties involving the golden mean. And so you could define a Kepler triangle as a triangle whose side lengths are in geometric progression. You could define a Kepler triangle as the triangle whose side lengths are the Pythagorean means of a pair of numbers. And these two numbers are special. Of course, you can get a scaled version, but if I scale it to a certain length, m turns out to be phi squared, and n turns out to be the reciprocal of phi. So phi squared and phi to the negative 1 power, or phi plus 1 and phi minus 1. I take phi plus 1 and phi minus 1. Those two things average out to the golden mean. The geometric mean is the square root of phi, and the harmonic mean of those two numbers turns out to be 1. So that's pretty cool. Okay, last thing.
Okay, I talked Troy into saving my favorite for the last.
Yeah, so the yin yang, is that how you say it? Yin yang?
Yep.
Ray speaks Chinese. So we've probably seen this this symbol, this figure. It has a lot of meaning. But I created the outer circle to have a radius of 1. So that red segment is close to 1. Again, it's the resolution and the way I construct, I'm dragging it. So that's as close as I get to 1, but we have a circle with a radius of 1. And then these smaller circles would have a radius of a half. So from AO is a half and OB is a half. But I'm going to drag point P, and it says drag point P to the location that makes the red segment the shortest length of the longest length. So as I drag point P, you see that segment getting shorter and shorter, and you see the numerical value up in the left-hand corner. It gets shorter to a certain point, and then it starts to get longer again. So if I can drag it to the place where it appears to be the shortest, it's going to go through that point A, and what do you notice there? That is the
Looks familiar.
reciprocal. And so now if I'm going to drag it so that red segment is the longest length, probably.
All right, what do you guys think this
surprising,
one will
but
be?
very surprising. It's going to go through that other point, and that's the longest length. So that segment becomes its longest length and its shortest length, and we see the golden mean appearing in the yin-yang symbol.
Troy, that makes me smile.
When Ray and I were coordinating our presentation, when I showed him this, he said, I keep thinking that I can't be any more amazed, and then I am.
Yep.
So
Thank you for sharing that philosophical example with us.
So I'm going to turn this back over to our host, Michael.
Well, thanks so much, Troy and Ray. As promised, we are going to be giving away to one lucky winner a TI graphing calculator of their choice. And tonight's lucky winner is Gerald Oberg. So, Gerald, congratulations. We'll be in touch over email to get a little more information from you about which TI graphing calculator you're going to choose. To receive a certificate of attendance, go ahead and click the link that is about to appear in the chat window. Also listed is a link for the documents that was used tonight as well. I know Ray made reference to those documents a couple times. So if you were to click on the documents link, you'll see lots of documents from tonight, my PowerPoint, etc. And there's also one that is titled Link to Documents, and that's really the one you want. That's the good stuff from Troy and Ray. So if those links aren't working for you for any reason, just hang tight. You'll automatically get a follow-up email in a couple days. That follow-up email is really great. It has a link to the recording from tonight, a link to the documents, and a link to the certificate as well. And if you're watching this on demand, go and copy this link into your favorite browser to receive your certificate. If you need to get a hold of us, give us a call, 1-800-TI-CARES, or drop us an email at ti-cares@ti.com. We would really love to hear from you. When you leave the webinar tonight, a brief survey will automatically appear in your browser. Your feedback really does guide us as we plan future online events, such as this one. So please share your thoughts in the post-webinar survey. Huge thanks to Troy and Ray. I thought I knew a lot, and you guys have humbled me as always. So thank you so much for everything you shared tonight.
Thank you. I agree with Annika. I agree with Annika. Math is truly beautiful.
Yes. Thank you. It was a privilege to share.
No doubt. And thanks so much to everyone for joining us tonight. We hope to see you back online next week. Have a great night.